be doing is, on this first page of the worksheet, is going through this simulation of what makes a sampling distribution of means. How is it formed so that we know that we can use this bell-shaped curve to do what we need to do? Because our goal is to understand how means operate and how these sample averages, how we can find probabilities with those. So what we'll do is kind of go through this first page, and simultaneously I'm going to run this simulation here. This is courtesy of Rice Virtual Lab. They have this nice simulation just to show you how the pieces fall together. But in terms of the calculations we do in class, you won't need to run this. It's just to get an idea of where all the information comes from. So first thing we want to notice here is this parent population. Parent population, this is our population data. This has everything. So we don't really have any context to it, just imagine this is our population data. You can see it has a mean of 16, the median's the same thing, which makes sense, it's nice and bell-shaped. Standard deviation is 5. So, in terms of the parent population, this is our population data, which means this is all of the data. That contains everything. Then our next window is sample data. And let's see what happens with the sample data. So we're going to run samples of size 25. So I'm going to switch this to 25. So let's see what happens in this sample data window when I take a sample of 25. What's happening is it's grabbing randomly from our population data. And with how our population data is formed, we're more likely to grab from in here. As we can see, most of the blocks are over there. However, there are these extreme values. They're just pretty unlikely, like we only got one that's that extreme. That's kind of an interesting point there. But mostly, we're landing where we expect to, where there's a high probability, and then as the probability decreases out, we don't see as many sample values there. But what we did is we grabbed a sample of 25. So that's what happened from setting that sample size of 25. We grabbed 25 random values. So what we're seeing in the sample data window, that's showing us randomly selected data from the population. And for us in this case, we have this sample size of 25 that we're using. We'll look into what happens when we change the sample size. So that's in the sample data window. Let's see what happened in the distribution of means window. So in the distribution of means window, this little block fell down, this bright blue block. And why that's there is while we have the sample data, they did is once they took that sample of 25, they averaged those values. And those values averaged to right where that little blue block is landing. So this distribution of means, if we run this again, which means we're going to be taking another random sample out of the population, high likelihood of choosing near the peak, low likelihood of being out in those tails, and then we average the values. So we see that second block fall down, and it's because it's a second mean. So these values that are landing here, they're sample means. It's like this is a possible X bar value, this is another possible X bar value. So we're collecting in this distribution of means window. It's a collection of sample means. So which are those X bar values? And in this case, we should be specific that these sample means are coming from a sample size of 25. So we have these three windows working together. First window is just our population. Sample data is creating just one sample, one random sample from that population. And in this distribution of means, we're collecting those sample means from those sample sizes of 25. So our whole goal here is to understand the behavior of means. That's why I want this distribution of means to see if we can calculate the probability of seeing an average from a certain sample size. So what we want to understand here is if we have some population data, if we kept running samples over and over and over again, what is the distribution of means? how do they behave? Because if they're nice and bell-shaped, which is exactly what we want, then we can start calculating probabilities. All we'd have to understand is the mean and the standard deviation of the distribution. So before we jump into running this simulation as close as we can to infinitely many times, let's see what's happening with our statistics over here. So we have this mean of 16 up here, and then we can see this mean coming through down here as well. In fact, it's not calculating it yet. I'm just going to hit this 5 button, and that's going to give us some more means. So basically, it just ran 5 more random samples and collected 5 more sample means. So now we have a total of 7 of them. So now we can see this mean of 11.48 coming through. So these means differ, and they differ right now because our sample size down here is very, very small. We're going to want to expand that. In fact, let's go for it. So I'm going to click this 100,000 button right here, and what that's going to do is it's going to run this 100,000 times. So with a nice click of the button, we now have 100,007 sample means collected here. And this is the idea of getting close to infinity. We took infinitely many samples. From here, how do all those sample averages behave? So what we can see is the means have the same value, but what they represent is very different. So let's go to answering our question here. Looking at the statistics at the left of each window, for each one, what exactly does the mean refer to, and why do they differ? So for the top window, the population data, this is how individual responses behave. Each thing is coming from a single person or a single thing. So we average, this is just our population average here. Population mean. We have population data, we average it, and gives us the mean. So for that parent population, where it has the wording mean, that's just our standard value for mu, that population mean. And that's based on individual values. We look down at the distribution of means. It's calculating the average of these values, and what it's averaging are all of the sample means that we're getting out. So we can imagine this is full of these X bar values, so we're averaging those X bars, averaging those sample means. So how we want to interpret that for our distribution of means, when we calculate that average, if we get to the point of running it as close to infinitely many times, it is going to be population data, so we're going to use that same population mean symbol. However, it's the average of sample means, so you put this little subscript of X bar to represent average of sample means. So it's the mean of the means in the end, which isn't great terminology, but it's the idea that we have all these X bar values, and if we average them, that would be the symbol that we use. So this gives us an idea of the center of the distribution. Let's also talk about the spread of it and the shape. So we have these many, many repetitions here, so there's 100,007 values here. If we describe the shape, this is a nice bell-shaped curve, which is exactly what we want. We can calculate probabilities and find cutoff values from these bell-shaped curves. So we have this nice normally distributed graph here. So that's going to come through from random sampling. We have our mean, which the mean ends up just being the same as our population mean. Because when we're grabbing these samples, on average, they're behaving in this region. You should keep averaging to the middle of this distribution most of the time. As we can see, there's a little variability. In terms of variability, our standard deviation is going to be smaller than our population standard deviation. And why that is if I run a sample, so we take a sample of 25 values, so mostly we're landing towards the middle here. But as you can see, ooh, this is a good one. I got an extreme value out here. I also have this extreme value here. Let's really focus on this one. This is quite unlikely to occur. So in terms of an individual value, if with that part of the parent population, it's counting that variability there. However, when we move to means, we're taking an average of these values. I kind of imagine it like a game of tug-of-war, so that while we have this one extreme value that's trying to pull the mean, in this case to the left, there's 24 other values that are pulling it back to where it should be. So with that, they're going to win. With 24 other values, they're going to correct this kind of extreme value. It's being taken into account, but it doesn't have that much influence. So these are the pieces that come through when we run this infinitely or close to infinitely many times. We see the shape is normally distributed, which is perfect. We want that. The mean of our distribution of means is the same as the population mean. So the centers of the two graphs are going to be exactly the same. And then what we'll see with standard deviation is that we'll have a smaller standard deviation. And this is because when we take averages, the extreme values aren't as effective. But while this was with a sample size of 25, let's see what happens to these pieces if I used a sample size of 5. Let's see what would change. So based on shape, mean, and standard deviation, if I switched over to sample size of 5, which means now it's grabbing 5 values randomly and collecting those averages. So as we can already see, there's less values coming through, and when they average, it's dropping down there. So let's press that nice 100,000 button, and what we can see is it's still normally distributed. That's perfect. Our mean is still the same as the population mean, because when we still grab these samples, they should be centering out to that middle there. Standard deviation is larger. When it was a sample size of 25, we actually had a standard deviation of 1 there, and now it's grown. It's still less than the population, and it's still less because when we take these samples, we're averaging. So we're landing closer and more centralized to that middle. However, it's grown from our last distribution of means because with these smaller sample sizes, it's like that game of tug-of-war. It's a little more even now. Let's see if I can get a good one with an extreme value. Oh, that's a very nice sample. And one more. Let's see if we can get a good one with an extreme value. All right, let's look at this scenario where this one's departed. We think about that game of tug-of-war. If we have this extreme value, now it's 1 against 4 values. So it's a little more even. Before it was 24 other values that would kind of pull the mean back to where it should be. But in this case, it would be that there's kind of 4 values behaving normally. And then if we have 1 extreme value, that can have quite a bit of pull. So that's where we're getting kind of this wider spread of possible means, is because these extreme values have more influence. So if n equals 25, smaller sample sizes will have larger standard deviations. It'll always be less than the population, but in terms of comparisons, large sample sizes will have small standard deviations, and small sample sizes will have large standard deviations. So all of this is from population data that was nice and bell-shaped. But let's look at what happens when I change the distribution. When I change it to a skewed distribution. So this is heavily skewed to the right here. Most of our data is on this left-hand side, and then the tail goes out to the right. So we still have this idea of mean and standard deviation. And what we want to do is compare what happens when we have a small sample size versus a large sample size. So let's go to an extreme of sample size of 2. I know the worksheet says 5, but let's switch it to a 2. And let's see what happens when we grab our, if we grab a single sample here, it's just going to grab 2 values and average those. You can see grab 2 values, average those. So let's see what happens when I run this 100,000 times. In terms of shape, center, and spread, we want to start with shape and notice that this is skewed data. This skewed data isn't going to help us out. We can't find probabilities with this, or at least we can't without some Calc 2 work. So to avoid calculus and kind of going with the technology we're using, this isn't going to work for us. So we want to be careful of the small sample size, and it's because when we have these small sample size, it begins that influence, that tug-of-war game, where if we get these extreme values, it's having a lot of influence. And with that, it's going to pretty much mimic what's happening in the population. Let's see what happens when we bump up our sample size. What happens when we go to a sample size of 25? So if I'm grabbing 25 values, now it's going to be that idea of probably about 24, 23 values where we expect to be landing, but then maybe we'll have some extreme values coming through. But it's that tug-of-war game that our center is at 8.08, and we should be averaging out there with these large sample sizes. So if I run that 100,000 times, here we go. Nice little bell-shaped curve. Mean is the same as the population, which is just like we saw before. And then we have this smaller standard deviation because we're taking averages. So this is showing the importance of sample size when we have skewed data, or basically just not normal data. And we want to be careful of this. So if we notice, so instead of 5, we use 2. If our sample size is small, the distribution of means is skewed. And we don't want that. That's not going to help that. If we take a large enough sample size, and something we'll talk about is that it should actually even be a little larger than this to guarantee the distribution of means is normal, which that is exactly what we want. So this importance of sample size comes through in giving us conditions in terms of being given some population data, some population information. When can we assume this distribution of means is bell-shaped so that we can use the tools that we have to calculate probabilities? And that brings through the central limit theorem. The central limit theorem gives us the conditions that we should check to make sure that we have a nice bell-shaped curve for this distribution of means. The first thing that we should have is this independence assumption, in that when we sample these values, they should be independent of each other. There shouldn't be any influence. Another way to check this is to look at that 10% condition, which the 10% condition just says if you're sampling less than 10% of the population, can assume you have independence. Randomization, our sample should be randomly chosen. We should be taking these random samples. Sometimes this won't be stated clearly, so sometimes we have to assume this. We're going to often assume they're good researchers and taking a nice random sample. And this last piece is our sample size condition. And then we should be taking large enough samples so that we avoid this case where with this sample size of 2, our distribution of means would actually be skewed. So there's kind of 2 scenarios. If your population is bell-shaped and normally distributed, you don't have to worry about the sample size. If the population is normally distributed, then no matter the sample size, I mean, we took a sample size of 5 with that normally distributed population data, and it was also bell-shaped. So it's just going to mimic that population data. So if it's bell-shaped, it stays bell-shaped. So this, the distribution of means is bell-shaped, is also normal, which is exactly what we want. So no real sample size condition there. We would just want to comment that population is normal too. For skewed distributions or anything that's not normally distributed, we need a large sample. As we proved here, the larger sample gave us that normal distribution. So if the population is not normal, we need to make sure we have a large enough sample size so that our distribution of means is normal. And the typical number that we use is that the sample size should be more than or equal to 30. That's kind of our go-to number. I mean, as you saw with 25, that was pretty bell-shaped, but 30 is the number that's going to be stated in more statistics books of minimum case, take a sample size of 30. So we always want to check those conditions before calculating with distribution of means to make sure we have this nice bell-shaped curve.